Okay, so after we are done with placement and CTS, next step is routing. The routing is a step where wires are created. When I say created, I mean physically created. And actually the more technical word for wires is nets. So I will stop using the word wires and I will use the word nets from now on. So nets are created in routing. Okay. So by the time we get to routing, the standard cells have been placed, clock tree has been implemented. Okay, so I'm just drawing this here to give you the, let's say that we have all these standard cell rows. And then we have standard cells that are placed all over. So I'm going to consider a bunch of, let's say that these three standard cells have to be connected. Okay, so we're connecting A. A is a driver. It's connected to B and C. Okay, and of course there are lots of other standard cells around. So I'm just showing A, B, and C. But let me use some other color. Let's say a gray color. There are lots of other standard cells. Okay, so let's say there's other standard cells here. Let me delete this. Okay. Sorry, I'm struggling to find the mouse. Okay, so I've got the other standard cells also, which I'm showing in gray, and the ones in black are the ones the router has to connect. Okay, so how will the router do the connection? So it's already the placement is there, and I have to connect using the different metal layers. So the router may choose in this case to connect metal to connect A, B, and C using, let's say, it'll start with metal 2. I'm showing in blue, and then it may go in metal 3, and then it may go in metal 2 again. And the pin that says it has to connect to is out here, so it knows where to go. And the pin for A that is connecting to is here, so it knows where to connect. And let's say the pin in C is out here. So then it will go, let's say it may do a metal 3 below there, and then it may have to go up to metal 4 for some reason, because there's other nets in that area, so it needs to go up to metal 4. Then maybe it goes back to metal 3, and then it goes to metal 2 again, and then metal 3 again, and metal 2, and then it has to go to metal 3. It has to get to the pin, so it goes back in metal 3, and it goes to metal 2 here to make the connection. And between all these different metal layers, there will be via. So there will be a via there, and then there will be a via here. There'll be a via here, and there'll be a different via out there. So all this, what I'm doing manually, will be done automatically. Okay. Now, one of the things you will notice when I was doing this routing to connect A, B, and C in different metal layers, you notice that all metal 2 lines are, metal 2 is horizontal. So you can see all the blue metal 2 is always horizontal. And the metal 3 is always vertical. And metal 4 is horizontal. And that is very fundamental to how a router works. So routers will have, so every metal layer will have a preferred direction. So metal 2, metal 3, metal 4, and they will be alternative. So if metal 2 is horizontal, metal 3 will be vertical, metal 4 will be horizontal, metal 5 will be vertical, and so on. Okay, so this is always the case in a technology, and that's how a router does. The software that does the routing, the software that creates these nets physically, will always route it will route using different layers of metal, and each layer of metal will have a preferred direction, and alternate layers will be horizontal or vertical. Okay, so that's one very important thing to note. So the reason I had to go when I went from this metal to here, and I wanted to get to this pin, I had to go vertically. So the router will have to go up in metal 3. It cannot just take this metal 2 and then just do everything in metal 2 all the way till here. It cannot do that. If it has to go vertically, it will go only using a vertical layer. And when it's going horizontally, it only go using a horizontal layer. This kind of topology is called Manhattan topology. Manhattan topology. And that's because if you see the Manhattan, which is an area in the city of New York, if you look at the roads in Manhattan, all the roads go horizontally and vertically. Kind of like in Bangalore roads, you have in various neighborhoods in Bangalore, you have means and crosses, and they go horizontally and vertically. That's the kind of geometry that a router can deal with. So all routers are Manhattan routers. All wires only run using metal layers that go horizontally or vertically. You will never have a wire going in some diagonal direction. There's never a wire that will go like that. Always horizontal and vertical only. That's called Manhattan topology. And the distance, say, between A and B, the distance, this is the actual distance between A and B. And and then there is something called a Manhattan distance, which is the distance that you would go when you go using a Manhattan topology. Okay, so every net will have a Manhattan, will have a distance. The distance or length. The length will always be a Manhattan distance, because all nets run only horizontally and vertically in different layers of metal. So going back now to the slides. So what have we done here? We have covered all the steps in place and route. Placement involves placing the standard cells. A floor plan is needed as an input. At the end after placement is done, we can distribute the clock, since all the locations of flip-flops is known. Once the clock is implemented, then we can go to routing. And in routing, the router, which is a piece of advanced software that will actually connect everything up physically using different metal layers that are available to it. What metal layers are available to it, it knows from the tech left. So what I've not shown explicitly as an input in this block diagram are the standard cell data that every one of these tools needs. I've not shown that with arrows here. All the arrows are only showing the design data. You have to keep in mind that in addition to all these design inputs, every one of these blocks here also gets technology input, which is basically information on the standard cells and the standard cell library. And that information is either .lib or left or both. Okay. So for example, what information will what standard cell files will the placement tool need? Well, it will obviously need the left of the standard cells, because it needs to know the dimensions of each standard cell, where the pins are, and so on. It actually doesn't need to know where the pins are, but it actually needs to know what the dimensions of the standard cells are, what's the width of each cell, so it can place it correctly. So the placement tool will need to know, will need to read the left. The placement tool also, because it has to be timing aware, it needs to have some awareness of delays. It also needs to read the .lib. And from the .lib, the placement tool will also know the functionality of each cell. Now, in principle, the placement tool does not need to know about the functionality. It just needs to know that which cell is connected to which other cell without worrying about the functionality, without bothering whether it's an AND gate or an OR gate. It just has to place them in a way that reduces the total length of nets and and optimizes timing. But today's placement tools are often very advanced. They can do some amount of logic restructuring. So when the synthesis tool generates a netlist, the placement tool can actually modify that netlist. It can, for example, convert a NAND gate into an AND gate and an inverter, just to take a simple example. But it can even do more complex logic restructuring. So it will not change. Obviously, it cannot change the functionality of the circuit, but it can change the structure of the circuit by re-implementing combination logic in other ways. And it may do that in order to optimize the results of the placement. During placement, if it finds that it's a better idea to implement some combination logic in some other way than what the synthesis tool did, it will make that change. And in order to be able to do that logic restructuring, the placement tool also needs to be aware of the functionality of each cell in the library, and that it gets by reading the .lib. So the placement tool has to read both the .lib and the left. Okay, the .lib will be used to be aware of timing as well as to do any logic restructuring if the placement tool is capable of doing that. The synthesis tool, it is important to note that the synthesis tool has no awareness of, it has no physical awareness. It is not aware of distances. It has no notion of cells being placed. It is merely creating a netlist with some estimates of load capacitances using wire load models, and it just optimizes the logic. The placement tool is fully aware of the physical picture. It knows how far things are. Then it has a better idea of the load capacitances, and it can therefore restructure the logic with some with physical awareness. So that can happen during placement. And then the router will finally connect everything up. So at the end of routing, the layout is complete. Okay, and then let's quickly go through the next few steps before we end this session. So once the routing is complete, we have to analyze if the circuit after the full layout is done is good. It meets our requirements. So after routing is complete, which marks the end of layout, we export some information from the place and route tool. Okay. So first of all, we export the layout of all the routes of all the routes. So all the nets and the layout is exported in the form of def, the same format that is used for the same file format that is used for this floor plan input can also be used for getting all the details of all the individual wires or the nets in the layout, which metal layers they are in, what is the entire geometrical picture of each net is captured in the def. So that's one export. The second thing that comes out of the routing at the end of place and route is a new netlist. Why is this a new netlist? What is the difference between the netlist 3 and the netlist 7? Well, in the netlist 3, the clock is ideal, so there is no clock 3. Then the placement tool will do some logic restructuring, so that also changes the netlist. So there is a change in the netlist after placement. There's a change in the netlist after clock distribution, because now the clock distribution will introduce the clock tree with all its buffers. There can be some small changes in the netlist by the router. The router may upsize some cells to more drive strength or less, or downsize some cells to less drive strength, and so on. And so in each of these steps, placement, clock distribution, and routing, the netlist gets modified. And then the final netlist is what is exported as 6. I mean, that's his output 7. Okay, that netlist can be then analyzed for timing. So you can take this 7, the net output netlist, and take it to a static timing analysis and check if the timing requirements have been met. To make that static timing analysis more accurate, what we do is we take the layout information that's in the def, this number 6, and we take it to a special software called an extraction tool, an extractor, which will determine the accurate resistance and capacitance of each net. Since the detailed layout is known and available in the def, the extractor will be able to now determine with high accuracy, determine the resistance and capacitance of each net. And that information is exported in a standard format called SPEF that you see here, that is called standard parasitic exchange format, because the resistances and capacitances are parasitic. And so this SPEF and the netlist in number that's in 7, they can go into the timing analysis tool. The timing analysis tool now knows accurately what the resistances and capacitances of all the nets are. It knows all it obviously has the entire netlist, and so it knows what all standard cells are there, and it can then determine the timing from one flip-flop to the other. See if the timing is met. If there are timing violations, then you have to fix them. If there are no timing violations, then in principle we are done. we can send the mask, we can send the layout information for mask making. But we also need to make sure that there are no design rule violations in the layout. So we have to do those design rule checks as well. That's what this physical verification step is. And once DRC and LVS is checked, DRC being design rule checks, LVS meaning you check the layout versus the schematic and make sure they represent the same circuit. You do those kind of checks, make sure that nothing has been messed up during place it out. And if everything checks correctly, then you're done and the chip can be sent to the foundry for fabrication.